Hello and welcome. This is Brian Avila presenting about frequency and amplitude modulation. So what are the objectives of this presentation? The objectives are to learn the difference between frequency and phase modulation, to expound the meaning of each of the terms on the different modulations, to learn how they work and what are the common uses, to know the different mathematical formulas used for each of the modulations. So what are the difference between AM, FM, and PM in terms of wave? So here are the waveform representation of each of the modulations. We have here the amplitude modulation, frequency, and phase modulation. So amplitude modulation can be also classified as a angle modulation. Angle modulation, it has two under it, which is phase and frequency modulation. So judging by this graphical representation, we can say that phase modulation and frequency modulation is related with each other. So what is a frequency modulation? It is the encoding of information in a carrier wave by varying the instantaneous frequency of the waveform. So it has more superior noise resistance than PM, which is phase modulation. So here is the formula for computing the FM. So we can see on this formula that frequency term have been replaced by a time varying frequency. So that frequency term is this FC, which is replaced by FC plus triangle F over V sub MO times V sub N times T. So where triangle F is the peak frequency of deviation. This means that FC now varies between extremes of FC minus triangle F and FC times plus triangle F. So this is the waveform to get the waveform frequency modulation. So here the plus C is a constant. So in other words, to get the waveform of a frequency modulation, you have to integrate. So here is a frequency waveform. So we can see here that frequency modulation is represented as a sinusoidal wave. Frequency modulation and index. So this is the formula for frequency modulation or index, where frequency deviation is used to describe the maximum difference between an FM modulated and nominal carrier frequency. And under it is the modulation frequency, where modulation frequency is the peak of the frequency deviation. So basically you are just getting the division of the frequency domain. So here in frequency domain, we are talking about time and different domains that is affecting the frequency modulation. So AM and FM usually have the same baseband and carrier signal because FM is under AM. So but this is changed when looking in the AM and narrowband FM, where narrowbanded FM involves a limited modulating bandwidth and allows for easier analysis. This means that when looking in a carrier frequency, not AM, the baseband's spectrum itself shift upwards, while in FM, the spectrum of the signal integral of the baseband signal that only appears on the band surrounding the carrier frequency. So this means that in AM it goes upwards, while in FM the spectrum is unknown, which is suggesting that getting the bandwidth of FM is more complicated because you cannot predict its bandwidth. So here is a graphical representation of that, where we can see that there is no point or number where is the same. And here we have MT stands for the modulates. MT is, while in the deviation ratio, it is the maximum permitted frequency deviation difference. It's also the difference between an FM modulated frequency and nominal frequency. This is the formula for a deviation ratio, where Fmax is the maximum peak frequency deviation and F sub M max is the modulating frequency. So now we are tackling about the Bessel's function, where it can be related to a FM. So what little history about Bessel's function is, it was first introduced by Daniel Bernoulli, then later then completed by Frederick Bessel. So Bessel's function is the canonical solution used to help differential equation. So canonical means it's a waveform but in circle. This is the formula. This is the formula for Bessel. Now, bandwidth of an FM or frequency modulation. A bandwidth of an FM is not as straightforward as the computation for AM. As we said earlier, that FM's bandwidth is much more harder to get because it is unpredictable. It can be computed using the Bessel or Carson's rule. So as we said earlier, Carson's rule can also be used on EM. So this is the formula for the Carson rule, where 2 times triangle F plus Fm, and this is the formula for Bessel table. So we can use Bessel table to get the Fm, where 2 times n x Fm max. F sub m is equals to maximum modulating frequency, and n is the number of significant